Okay, well, good afternoon in South African time to everyone, or good morning, good evening to attendees from other parts of the world. I would like to take this opportunity to thank the ISA for the invitation to present this talk today. I'll be discussing Africa's contribution to global mineral supply with a focus on minerals beneficiation. So firstly, looking at Africa's commodity production and reserves and using the latest figures from the USGS commodity summaries, I've plotted the percentages of global mine production and the percentages of global reserves that are contributed by African countries. For global production, we see that the top 10 commodities account for more than 40% of global production coming from African countries. And this can be as much as 83%. Andalusite, platinum group minerals, specifically platinum, then manganese, vermiculite, and chromium are predominantly produced by South Africa, whereas cobalt and tantalum come predominantly through production from the DRC. Sierra Leone produces the majority of rutile, whereas industrial diamonds and gem diamonds are predominantly produced by the DRC and Botswana, respectively. When it comes to the percentage of global reserves, we see that the top 5 commodities coming from Africa account for more than 42% of global reserves. And these are platinum group minerals, phosphate rock, which comes from Morocco predominantly, and then cobalt, manganese, and industrial diamonds. Now, South Africa's mineral wealth contributes a lot to African production, with the world-famous Bushveld complex accounting for the majority of platinum group minerals, vanadium, and chromium. The Witwatersrand Basin accounts for world-class gold and uranium deposits. The Phalaborwa complex gives us vermiculite, phosphate, and copper. The Kalahari manganese field accounts for the majority of the world's land-based resource of manganese, along with some iron deposits. And in the eastern part of our country, we have coal deposits. We're also quite famous for diamond deposits from our kimberlite pipes, our alluvial deposits, and offshore deposits. And then we also have titanium and zirconium from our east coasts and west coasts of the country. Now, against this backdrop of a large abundance in mineral resources, the minerals value chain is an important one in not only producing raw materials through exploration and mining activities, but also through beneficiation of these commodities. Now, to promote this beneficiation and thereby the unlocking of South Africa's mineral wealth, and indeed that of the African continent, South Africa has a National Science Council called Mintek. And we have advanced facilities to conduct research and to do test work in developing appropriate process flows that will concentrate and extract, refine, and add value to various commodities from across the world. And we report to the Department of Mineral Resources and Energy in the South African government. We've been in existence for more than 87 years now, and our campus is located in Randburg in the Gauteng province in South Africa. So you can see from these buildings here where we house our laboratories, but also these larger buildings where we house bays where we conduct test work. Now, in order to conduct our work, there are several technical disciplines that are involved, from ore characterization and mineral processing through to extractive metallurgy, and then automation and advanced materials. For beneficiation work, the first step is to know your ore. And this is about a lot more than just the grade of the ore. Minerals are ultimately what we process, so we need to know which minerals host the commodity of interest and which minerals we are not interested in. For this purpose, we have one of the most comprehensive laboratories for characterization on the continent, certainly the most diverse in terms of the instrumentation that is available for process mineralogical studies. These are high-end, cutting-edge pieces of equipment, and they allow us to understand our ores much better so that we can find the best ways in which to process them. The next step is typically that of minerals processing, and this covers comminution, which is the crushing and the milling of the ores to produce particles. We can additionally do physical separation, which exploits the physical properties of minerals to separate them from one another. And here we make use of sensor-based sorting methods, as well as gravity and magnetic separation, as well as classification. Flotation, on the other hand, is a technique that relies on the surface properties of particles to separate them. And here we do test work that services our platinum group minerals industry. We can also do base metal and industrial minerals recovery through flotation by froth use. Now, there's no chemical change that is imparted to the ore to a great extent. We can undertake test work from laboratory scale through to the pilot plant scale, as you can see from these banks of flotation cells in one of our bay areas. For extractive metallurgy, chemical changes are imparted to the ore when we extract and when we refine the valuable commodity. This is typically done from mineral concentrates. Now, some aspects of hydrometallurgy include pressure oxidation, which we make use of for the recovery of gold from refractory ores. We also do precipitation and cementation, ion exchange, and then solvent extraction. And in this regard, we have built a test facility for rare earth element separation and purification that comes in as a step after the leaching of concentrates. And we have developed various flow sheets to handle rare earth element deposits from many parts of the world. Direct cobalt electrowinning is a patented technology that is important for cobalt recovery that we've developed. And increasingly, we make use of digital twinning for modeling and simulation studies that are related to test work from laboratory scale, again, all the way through to plant scale. Our pyrometallurgy facilities are also available from laboratory to pilot scale, and we have a global footprint in direct current furnace technology. We have 1.5 megawatt and 3 megawatt furnace capacity on site, and you can see these people that are dwarfed by the furnaces and all the constructions in one of our bay areas. In all of the work that is conducted, we make use of modeling and simulation, which plays a large role in controlling furnace conditions. And we've had a number of different technologies that we've developed. Some of the key ones include nickel laterite smelting in a direct current furnace. And the image up here shows a DC furnace facility that was constructed by Xstrata Nickel for the Koniambo ferronickel smelter in New Caledonia. And this facility was commissioned in 2013-2014, but it was based on technologies and test work that was conducted at Mintek. So we do have an international footprint when it comes to our pilot scale activities. Cobalt recovery from slag using DC furnace technology is another key aspect that we've developed. And another one of importance is that of py-earth. This makes use of smelting as a pre-concentration step when we treat ferruginized or iron-rich lateritic rare earth element ores. And in this process, the rare earths report to a slag, whereas we can produce a pig iron as a byproduct. The rare earths are then recovered from the slag by leaching. Another important project that we're busy with currently is an EU-funded one where we're conducting research into the reduction of carbon emissions as well as energy consumption in the pre-reduction of manganese ores. And given the fact that South Africa hosts the world's largest land-based resource of manganese, this is of obvious importance to the country. We've also developed smelting and leaching technologies to recover precious metals from electronic waste. For beneficiation, we also develop process control technologies. In other words, we look at advanced online computational workflows that will ensure consistent performance on a process plant when it needs to handle feed variability coming through from the mining. And these technologies have been developed for milling, flotation, smelting, and gold leaching. We've commissioned our technology at more than 300 sites worldwide in countries shown in orange on this global map. Now, our work also takes into account circular economy and zero waste principles. We're not only looking at efficient processing, but also in extracting value from waste that has been derived from previous processing steps. And we look at minimizing the contamination, what is left over, so as to be environmentally acceptable. So to conclude, Africa contributes significantly to global commodity requirements. However, we are not only exporters of raw materials. We have developed cutting-edge technology to beneficiate these commodities. We cover the entire minerals value chain, whether it's through characterization for the purpose of exploration and mining activities, whether it's for concentration, extraction, refining, and value addition to these commodities. But in all of these endeavors, we strive towards the optimal use of our resources and waste minimization. Our technologies have not only been used to develop our own world-class ore deposits, but they've also been applied to ore types worldwide. And in this respect, the flow sheets that we develop and the test work programs that we undertake would be equally applicable to the optimal processing of seabed deposits. And with that, I'd like to thank you for your attention.